Hello and welcome. Today we are dealing with the Cayley-Hamilton theorem. This is a theorem in linear algebra. It was founded by two mathematicians, namely we have Cayley and the other one was called Hamilton. And the theorem states that every square matrix over a commutative ring, such as the real or complex numbers or the integers, satisfies its own characteristic equation. And a square matrix has the number of rows is equal to the number of columns. That's when we call that matrix a square matrix. Another statement of the Cayley-Hamilton theorem states that every matrix, that's another statement, every matrix A, n by n, we are saying n by n because it's a square matrix, is a zero of its characteristic equation. Is a zero of its characteristic equation. That's the statement, or rather characteristic polynomial, not just equation. That means P A of A will give us a 0. For example, we are given a matrix A. This matrix is a 2 by 2 matrix. We have 2, 2, negative 1 and 1. Then we are asked to use the Cayley-Hamilton theorem to find the inverse of the matrix. The first thing will be to get the characteristic polynomial. We have lambda 0, 0 lambda. We subtract 2, 2, negative 1, 1. That gives us a value here. We have lambda minus 2. We will have positive 1, negative 2, lambda minus 1. Lambda minus 1. And now we have to get the characteristic polynomial. This will be the gradient, not the gradient rather, but we are finding the determinant. So we are going to use the correct brackets, or rather you're going to use straight lines because you are finding the determinant. And the determinant of a 2 by 2 matrix, we are saying the leading diagonal minus the other diagonal. We will have lambda minus 2, lambda minus 1, minus 2. That gives us lambda squared minus 2 lambda, lambda squared minus, not minus 2 lambda, there's something we have forgotten here. We will have lambda minus lambda minus lambda minus 2 lambda plus 2 plus 2, because this will give us a plus. That gives us lambda squared minus 3 lambda plus 4, and that's our characteristic polynomial, of which we get from we get from getting the determinant here. And now our next thing, we are supposed to apply our Cayley-Hamilton theorem and get the inverse. We want to get A inverse. But now by our Cayley-Hamilton theorem, we are saying that if we take back A in the characteristic polynomial, we are supposed to get a 0. That means to get our PA of A, wherever we have a lambda, we are putting A. We will have A squared minus 3A plus 4I is equals to 0. And now we are asked to get A inverse. We will pre-multiply both the left and the right with the inverse. We will have A inverse into A squared minus 3A plus 4I is equals to A inverse times 0. That means when you multiply A inverse by A squared, you'll be left with A minus 3I, because we know that A inverse times A gives you I, plus 4A inverse, it gives you 0. But now here we have to make A inverse the subject. That means we will have 4A inverse is equals to 3I minus A. A is positive here. When it crosses the bracket, it becomes a negative. And now we are going to get divide by 4. But now here we see that A inverse is equals to a quarter into 3I minus A. We need to get the real value of the inverse. We have our A, we have our I. That means we're going to have a quarter into 3 times I. If we multiply 3 by I, we will have an identity matrix with 3 in the diagonal minus A. Our value for A was 2, 2, negative 1, 1. The value we get here for A inverse will be a quarter into 3 minus 2 gives us 1. 0 minus minus 1 gives us positive 1. We will have negative 2, and then we will have 3 minus 1 is 2, which is the same as a quarter minus a half, a quarter, a half. And now that's our value for A inverse using the Cayley-Hamilton theorem. That's for a 2 by 2 matrix. We can try one for a 3 by 3 matrix. For example, we have been given that A is equals to a 3 by 3 matrix. Remember, we're dealing with square matrices, so the number of rows and the number of columns must be the same. We have negative 1, 1, 0, 0, 1, 1. That's our matrix A. Remember, our Cayley-Hamilton theorem states that if you're going to have PA of A, meaning that every matrix is a 0 of its characteristic polynomial, and it being a 0 means that if you substitute it back in the characteristic polynomial, you're supposed to get a 0. Our first thing, as usual, is to get our characteristic equation. And to get a characteristic equation, we are going to subtract. We are going to use the equation lambda I minus A. We need the polynomial, so we will have lambda. This is an identity matrix with lambda in the main diagonal, 0, 0, lambda, and then we subtract with the A that we have, and our A is 1, negative 1, 0, 0, 1, 1, 0, 0, 1. That gives us a characteristic polynomial. We are aiming at a characteristic polynomial. So we are going to get the determinant. We have lambda minus 1. We have 1, 0. We will have 0, lambda minus 1, negative 1, 0, 0, lambda minus 1. We are taking the determinants. And you know, when you're getting the determinant, you're supposed to use the row that's easiest, or the column that's easiest to give you the value. In our case, we have a column here, so we are going to use this first column, meaning that we block the first column, first row, first column, like that. We will have lambda minus 1. If you block the first, now our column is the basis, we block the first column, first row, we're going to be left with lambda minus 1 into lambda minus 1 again. the rest is 0 0. That means we will have plus 0 plus 0. We're going to get lambda minus 1 cubed, which is the same as lambda cubed minus 3 lambda squared plus 3 lambda minus 1. That's our characteristic polynomial. But now when we apply the Cayley-Hamilton theorem, that means we will have, wherever we have a lambda, we replace with a, we will have a cubed minus 3a squared plus 3a minus 1. We are supposed to get a inverse. But now this was supposed to be minus 1, now it becomes minus I. Because 1 is the identity, and you know you're replacing with a, that means you have I is equals to 0 according to the statement of our theorem. Now we want to get a inverse, means we pre-multiply through by a inverse plus 3a minus I is equals to a inverse by 0. That gives you a squared minus 3a plus 3I minus a inverse. Minus a inverse is equals to 0, because here it's I, because we said a inverse by a will always give you identity matrix. We have to make a inverse the subject. That means we will have a inverse minus, we will have a inverse is equals to, sorry, that's, we have to delete that, a inverse, we are making a inverse the subject. We will have a inverse is equals to 3a is equals to 3a minus, we're going to have 3a, we're making a inverse to be the subject. That means we have a squared minus 3a plus 3I is minus, okay, we will have 3, we will have 3a will be minus, we will have minus 3a minus a squared, or let's just go the correct way, because you remember we have our a inverse is negative, so everything that goes to the other side we negate. We will have a inverse is equals to a squared minus 3a plus 3I, because on this a squared will go to the other side, it will become minus, this one will become positive, the other one will become negative, and when we multiply by the negative here, we divide by the negative, it will go back to this normal state of a inverse minus 3a plus 3I. And now to get a inverse, we have to substitute whatever we have a, we put the inverse of a. We will have not the inverse of a, but rather the square of a. But now we have a squared, and if you take a squared, you will get 1, negative 2, negative 1, 0, 1, 2, 0, 0, 1. That's the square of a. A squared is just simply a times a, meaning you're multiplying the matrix a by itself, minus 3 into a, which is 1, negative 1, 0, 0, 1, 1, 0, 0, 1, plus 3I, which is 3 into, which is just 3 into 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you solve that, it gives you a 3 by 3 matrix, which is 1, 1, negative 1. We're going to have 0, 1, negative 1, and 0, 0, 1. This is 1, and that's our inverse using the Cayley-Hamilton theorem. Thank you and bye.